Hi all. How are you all? So in this session, we will continue our pumping lemma. This is part 4 of pumping lemma. In this session, what we are going to study? We will study what is the proof of pumping lemma. We have already seen pumping lemma for regular languages. We have already taken many questions, many examples. Okay. And I know you are very comfortable in pumping lemma. Okay. Most of you are very comfortable in pumping lemma. And some of you are, I can say 80% confident in pumping lemma. Okay. Anyway, the point is we have already seen what is pumping lemma. We have already taken examples, questions, everything we have already done. But now we need to see what is the proof of pumping lemma. Means why regular languages will satisfy pumping lemma. This is what we need to study. Okay, what is the proof? Then we will see some questions which are based on the proof. Means some questions can be created which are based on the proof. If you don't know the proof, those questions you cannot solve. Okay, so these type of questions also we will see. Then we will see what are the types of questions are possible in pumping lemma. All the types of questions we will solve. Okay, so this is our purpose for this lecture. Now let's start. We have already seen what is pumping lemma. So this concept, the pumping lemma concept, we have already seen. Now let's start. Pumping lemma proof. This proof is important, but this proof is actually very easy. Okay, let me tell you. See, many people, they will tell you that for GATE exam, proof is not required. You can skip the proof. Okay, you can by heart the formula, you can skip the proof. Many people will tell you that proofs are not required. But the point is, some proofs are required, some proofs are important. Okay, this is one of those proofs. So this proof is actually important. As I told you, there are some questions which you can solve only if you know the proof. If you don't know the proof, then you cannot solve. Okay, so this proof is actually important, but the proof is actually very easy. So let's start the proof of pumping lemma. Before we start the proof of pumping lemma, we need to make some observations about DFA. Do you know about DFA? Do you understand DFA? So some observations about DFA we need to make. So let's start with our first observation. This is our observation about DFA. Read this observation and tell me, do you know that this observation is true? This observation is saying DFA goes through a unique sequence of k plus 1 states when you run it on any string of length k. So if you run any DFA, whatever DFA you take, if you run this DFA on a string of length k, then this DFA will go through a unique sequence of k plus 1 states. This is our observation number 1. Let's see example. Let's see this observation using example. Okay, with the example, we will try to understand this observation. So let's see. This example you take. This DFA is given to you. First you tell me, is this a DFA? This finite automata that is given to you, is this a DFA? Is this deterministic finite automata? You check. What you will check? This finite automata, is this DFA or not? What you will check? You will check that every state on every alphabet symbol should have exactly one transition. This is your alphabet 0, 1. You can notice every state on every input symbol, there is exactly one transition. You can notice from this Q0 on symbol 0, there is exactly one transition. Okay, on symbol 1, there is exactly one transition. So very simple. This is a DFA. This is a DFA. Now, if you run this DFA on this string, tell me where you will start. Where the DFA will start? The DFA will start in the start state. This is the start state. So the DFA will start in the state Q0. Okay, you will start in the state Q0. Then tell me where you will go. From Q0, you will start. In this state Q0, you read this symbol 0. Then where you will go? In this state Q0, if you read the symbol 0, then you will make transition to Q1. So you will go to Q1. In this Q1, if you read symbol 1, where you will go? In this state Q1, if you read symbol 1, you will go to state Q2. In this state Q2, if you read symbol 1, if you read this symbol 1 in state Q2, then you will go to state Q3. In this Q3, if you read this symbol 0, in this Q3, if you read symbol 0, then you will go to state Q1. In this state Q1, if you read symbol 1, see, in this state Q1, if you read symbol 1, you will go to state Q2. In this Q2, if you read symbol 1, you can notice in this Q2, if you read symbol 1, you will go to state Q3. And in this state Q3, if you read symbol 1, in this state, if you read symbol 1, you will go to state Q4. Okay, yes or no? So can I say that your DFA is going through a sequence of states? Can I say on this string, take this string W, on this string, the DFA is going through a sequence of states. In this sequence, state can repeat or not? In this sequence, state can repeat or not? Yes, state can repeat. For example, this Q1 is repeating, no problem. For example, this Q2 is also repeating, no problem. This Q3 is also repeating, no problem. So states can repeat. Okay, but the point is, understand the point that if you run this DFA on this string, this is your DFA. If you run this DFA on this string, when you run this DFA, you will start in state Q0. Then tell me, will you go through a unique sequence? The sequence will be unique, right? The sequence will be unique. This sequence will be unique. Can you get any other sequence? Like this sequence you are getting. See, when you run this DFA on this string, your string was 0, 1, 1, 0, 1, 1, 1. This was your string. So when you run this DFA on W, this DFA, when you run on W, then tell me, what is the sequence you are getting? Just tell me the state sequence of states. What sequence you are getting? Tell me. Which sequence you are getting? You are getting this sequence. You are starting in state Q0, then you are going to state Q1, then you are going to Q2, then you are going to Q3, then you are again going to Q1, then you are going to Q2, then you are going to Q3, and then you are going to Q4. You tell me one thing, this sequence you are getting, agree? You are getting this sequence. When you run this DFA on W, you are getting this sequence. Tell me one thing, any other sequence is possible for this string? For this string in the DFA, any other sequence is possible? Is there any other sequence possible? No. DFA is deterministic. DFA is deterministic. So this will be unique sequence. This sequence is unique. I can say this sequence is unique. Okay. Did I say sequence is unique or did I say states are unique? In this sequence, states are unique or did I say sequence is unique? Yes, sequence is unique. States can repeat. States can duplicate. States can be duplicated. Yes or no? I am not saying states are unique. I am saying sequence is unique. States can be duplicated. Okay, states can repeat. But the point is, you are getting a unique sequence. This unique sequence you will get. And why you are getting this unique sequence? What is the reason? What is the reason why you are getting a unique sequence? But what is the reason you are getting a unique sequence? Because it is deterministic. Because your DFA is deterministic. Okay, because you have a deterministic finite automata. So DFA is deterministic. So that is the reason you are getting unique sequence. Okay, very simple. I hope this point is clear. So remember, can I say any DFA on any string will go through a unique sequence of states? This is the final point. Okay, very simple. So you can easily notice this is your string and this will be your state sequence. For this string, this is the state sequence. You can check it out. Okay, very simple. So I can give you any string. Okay, let me give you, for example, if I give you this string, let me give you another string. Take this string 0, 1, 1, 0, 1, 0. Tell me. Okay, next, let's see 1, 1. Now tell me, this is the string I am giving you. Now you tell me what will be the state sequence. When you run this DFA, let's call this DFA M. When you run this DFA M on this string, then what will be the state sequence? You are running this DFA. So then what will be the state sequence? Tell me the state sequence. Which state sequence you are going to get? What will be the state sequence that you will get? So tell me. The state sequence will be, you will start in which state? I am asking state sequence. I am not asking what is the last state. I am not asking. I am asking what is the state sequence. See, you will start in the state Q0. This is your starting state. In this state, if you read symbol 0, you will go to Q1. In this state, if you read symbol 1, you will go to Q2. In Q2, if you read symbol 1, you will go to Q3. In Q3, if you read symbol 1, you will go to Q1. In Q1, if you read symbol 1, you will go to Q2. In Q2, if you read symbol 0, then you will go to Q5. In Q5, if you read symbol 1, you will go to Q5. In Q5, if you read symbol 1, you will go to Q5. So this is the sequence we are getting. Okay, is this a unique sequence for this string? For this string, is this the unique sequence? Yes, this is the unique sequence. Yes or no? Agree? So this is the state sequence. So you can notice this is a unique state sequence we will get. This is a unique state sequence. or I can say unique sequence of states. You are getting a unique sequence of states. Okay, very simple. So this is the unique sequence. Tell me, in this sequence, how many states are there? Don't count count all the states. Okay, don't count I can say unique states, count all the states. So tell me, what is the length of this sequence? Tell me the length of sequence. In this sequence, how many states are there? The length of this sequence. And what is the length of W? You also tell me the length of W. See, the length of W, if you notice, the length of W is 8. The length of W is 8. What is the length of this sequence? The length of sequence, that is 9. The length of sequence, you can count, that is 9. You can count. Okay. The length of the sequence is 9. Similarly, in this also, what is the length of this string W? What was the length of W in this string? This is your string. The length of W was 7. And what was the length of sequence? What was the length of sequence? Sequence of states. Tell me, what was the length of sequence? How many states are there in this sequence? In this sequence, how many states are there? There are 8 states. Okay, now let's move on. So is this observation clear to everyone? That if you have any DFA, with n states, whatever DFA you take, for any string W, any DFA will go through a unique sequence of states. Is this clear? Very simple observation. Every DFA on every string will go through a unique sequence of states. So this is the idea. Okay, here also for this string, this is your string. What is the length of the string? The length of this string, that is 6. Tell me, how many states will be there in the state sequence? Tell me, in the state sequence, you will get a sequence of states. You will get a sequence of states. And what will be the length of that? The length of that will be 7. Yes or no? You can easily notice what will be your sequence. So if you run this DFA M on W, you will start in the initial state Q0. From Q0, when you read symbol 0, you will go to Q1. From Q1, when you read symbol 1, you will go to Q2. In Q2, if you read symbol 0, you will go to Q3. In Q3, if you read symbol 1, you will go to Q0. In Q0, if you read symbol 1, you will go to Q3. In Q3, if you read symbol 0, you will go to Q2. So this is the sequence you are getting. Again, you are getting this sequence you are getting. This is a unique sequence that you will get. And what is the length of this unique sequence? How many states are there in this sequence? In this sequence, how many states are there? That is 7. Okay. So this is the point. I hope all these points are clear. So this is the simple observation you can easily make. Okay. Similarly, you can notice this example also. In this example also, you can easily check. Just check it. If this is your string, then if you run this machine M on this string, then again what will happen? Your DFA will start in the initial state. In the initial state, when you read symbol A, then where you will go? When you read symbol A, you will go to state Q. In this state Q, if you read symbol B, you will go to state Q, you will go to state Q, you will go to state Q, you will go to state Q. So this is your string. The length of the string is 5. What is the length of the sequence that you are getting? What is the length of sequence that you are getting? That is 6. Okay. So in the what is the length of sequence? Length of sequence, that will be 6. You can check it out. And again, you are getting a unique sequence. This unique sequence you are getting. Okay. Again, you are getting this unique sequence. This unique sequence you are getting, whose length is 6. The string length is 5 and the length of sequence is 6. Okay. So very simple. This is the simple point. So this is your final observation. I can say that your final answer, your final observation, this is the final observation. You have a DFA. In that DFA, whatever string you take, then this DFA will go through a unique sequence of these many states. Yes or no? This DFA will go through a unique sequence of these many states. Okay. So your DFA can have any number of states. Tell me, this sequence will have these many states. Does it depend on number of states in DFA? Does it depend on number of states in DFA? No. Okay. No. You can easily notice. So that will only depend on string length, the length of the string. Okay. So this unique sequence you will get, and the length of this unique sequence, will be length of string plus 1. Okay. You tell me one thing, just small thing I'm asking. this formula that you are getting for any string W, is it also true for empty string? This formula that you are getting a formula. This formula you are getting for string W. For string W, you are getting this formula. Is this also true for empty string? Yes, this is also true for empty string. For example, this is your DFA. If you run this DFA, let's call this DFA M. If you run this DFA, let's call it M. So let's see this. Run this DFA M on empty string. Okay, let's run this DFA M on empty string. Tell me which is correct. Is this correct? You start in Q0 and you go to Q0. Is this correct? Is this correct? Is this correct? If I write like this, is this correct? Is this correct? See, the length of empty string is 0. So what should be the answer? The length of empty string is 0. So what should be the length of sequence? What should be the length of sequence? What should be the length of sequence? The length of sequence should be 1. Should be 1. But you are getting, if you are saying this is correct, if you are thinking this is correct, then you are getting length 2. Sequence length 2. Sequence length 2. This is absolutely wrong. Okay, this is wrong. Do you remember what I told you? How do you put this empty string on input tape? How do you put this empty string on input tape? How do you put? On input tape, how do you put this empty string? Will you put like this or will you put like this? Will you put like this, first or second? This is wrong, this is correct. I told you, if you remember, in the first class, finite automata first class, I told you. This empty string on input tape, how will you put? So on input tape, there is nothing. Because on input tape, you only put the alphabet symbols, yes or no? On input tape, we only put alphabet symbols. We can only put alphabet symbols, yes or no? These alphabet symbols we can put. We can only put alphabet symbols. Empty string is not an alphabet symbol. On the input tape, you will only put alphabet symbols. Is this point clear? So don't do like this. Okay, this is what the input tape will look like. If you put empty string on the input tape, this is what it will look like. So actually what will happen? See, actually what will happen on the input tape, there is nothing. On the input tape, there is nothing. So you will start in Q0, that's it. That's it. Okay, there is nothing to read. There is nothing to read. There is nothing to read. There is nothing to read on input tape. On input tape, there is nothing to read. Is this point clear? Okay, so you can notice. So this is correct. So you can easily notice your length of empty string is 0. So length of sequence should be 1. So length of sequence should be 1. And yes, it is 1. Length of sequence should be 1. Yes, it is 1. Now, is this point clear? Please tell me, is this point clear? So remember, if you think like this, if you are thinking like this, that is wrong. Actually, this is what happens. Actually, sorry, this is what happens. Actually, that's it. This is what happens. Okay, is this point clear? So you can easily notice a simple observation that length of empty string is 0. So the length of sequence should be 1. The length of sequence should be 1. It should not be 2. If you do like this, then length of sequence is actually 2. Is this point clear? Okay, agree? So very simple. So this is the idea. So anyway, for all strings, this will be true. So this is the simple point. This is the simple point. Any DFA, you can take whatever DFA you want. Any DFA you take, any DFA, any string. Okay, any DFA, any string. Any DFA, any string W. Okay, if you run this DFA M on W, then run this DFA M on W, then tell me what will happen. We will get this DFA will go through a unique sequence. DFA goes through a unique sequence. DFA will go through a unique sequence. Unique sequence of how many states? Of exactly length of W plus 1. These many states. Okay, so a unique sequence you will get, and the length of that sequence will be length of W plus 1. These many states. Okay, I hope this point is clear. And this is true for any string. You can take any string, empty string or whatever string, and you can take any DFA. This will happen. Okay, whatever DFA you take. So this is the simple point. Now tell me the answer for this question. I'm asking, DFA has n states. Okay, DFA has n states and string has length t. DFA will go through a unique sequence. We already know how many states are there in this sequence. Means what is the length of this sequence? What is the length of this sequence? These are the options. Tell me which option is correct. MCQ. Let's assume this question is MCQ. Only one option is correct. Which option will be correct? Which option will be correct? Tell me. Which option is correct? So the answer will be exactly t plus 1 states. The answer will be exactly t plus 1 states. Not more than this, not less than this. Not more than this, not less than this. Exactly t plus 1 states will be there. Okay. The length of W, that is t, exactly t plus 1 states will be there. Is this point clear? So this is your answer. Okay, so that's it. This is your observation 1. Observation 1 is done. Observation 1 is over. Explanation of observation 1 is over. So tell me, are you comfortable with observation 1? Did you understand this observation 1? All the examples, the explanation I told you. So this is your observation 1. You can notice every DFA goes through a unique sequence of k plus 1 states when you run it on a string of length k. That's it. Now let's see one observation about pigeonhole principle. Okay, let's make this observation. So this is the observation. Let's assume the DFA has n states. Okay, DFA only has n states. Now, if I give you any sequence of at least n plus 1 states, remember DFA has n states. If I give you any sequence of at least n plus 1 states, can you guarantee that some state will definitely repeat? Can you guarantee at least one state will definitely repeat? Yes, pigeonhole principle. For example, if I give you these states, let's assume your states are, these are the states, P, Q, R, S. Okay, how many states are there? Tell me. This is your set of states. So what is the set of states? Number of states is 4. Okay, now you tell me, if I give you a sequence of states, consider any sequence of these many states. How many? Consider any sequence of these many states. Any sequence, whatever sequence I give you. Okay, can you create a sequence of these many states without repeating any state? Means don't repeat any state. Do not repeat any state. Can you create a sequence of length 5? Can you create a sequence of length 5? Can you create a sequence of length 5 without repeating any state? You cannot create. Okay, so I can say some state, at least one state will repeat. Agree? Whatever you do, at least one state definitely repeats. At least one state occurs. How many times? Tell me, at least one state occurs how many times? At least 2 times. At least 2 times. Okay, yes or no? At least one state occurs at least 2 times. Whatever you do, you can do whatever you do. For example, if you do, then also you can notice. For example, if you do this, then also you can notice at least one state is occurring at least 2 times. Whatever you do, it will happen. For example, P, P, Q, P, P. Here also you can notice that at least one state repeats at least 2 times. Which state is repeating at least 2 times? Which state is repeating at least 2 times? P. P is repeating at least 2 times. Okay, so whatever you do, it does not matter. It does not matter whatever you do. For example, if you do P, Q, R, S, Q. Okay, see, whatever you do, it does not matter. P, Q, R, S, Q. Here also you can notice what is happening. Which state is repeating at least 2 times? In this, which state repeats at least 2 times? That is Q. Okay, so whatever you do, it does not matter what you do. It does not matter what you do. At least one state will repeat more than, I can say at least one state repeats at least 2 times. Okay, so this is your simple point. Is this point clear? This is a simple observation, pigeonhole principle. If I give you any sequence of greater than or equal to 5, these many states. Okay, if you have this is your sequence. if this is your sequence, then in this sequence, what will happen? Tell me. What you can guarantee for this sequence? You can guarantee that at least one state, okay, at least one state repeats at least two times. Repeats at least two times. Yes or no? At least one state will repeat at least two times. So this is your simple observation. So observation number 2, that is over. Is this clear? Pigeonhole principle. Very simple pigeonhole principle. Okay. You have 4 elements. You only have 4 elements, A, B, C, D. And if I tell you, give me a sequence of 5 elements. From this, give me a sequence of 5 elements. Then at least one element will have to repeat. Yes or no? Agree or not? If I tell you to give me a sequence of 5 elements from this, then at least one element, definitely at least one element should repeat. Okay. So this is your pigeonhole principle. Now let's see observation number 3. Okay. This observation number 3. Let's mix these two, pigeonhole principle and DFA. Let's mix these two. Okay. This is quite interesting. You tell me, you have a DFA. Let's assume DFA has n states. Okay. So please understand this. You have a DFA which has n states. You run this DFA and let's assume you have a string. You have a string n which has how many symbols? N symbols. Okay. So the length of this string is also n. Let's assume. Okay. You have a string whose length is also n. Now what you do? You run this DFA on this string. You run this DFA. You have a DFA m. You run this DFA on this string. You will get a sequence of state. You will get a unique sequence. Yes, correct. You will get a unique sequence. You will get a unique sequence of states. Okay. What will be the length of that sequence? What will be the length of that sequence? What will be the length of that sequence? That will be n plus 1. That is the length of W plus 1. Okay. That is the length of W plus 1. I can say length of W plus 1. That is n plus 1. Okay. So you will get this sequence. You will get in this sequence. There will be how many states in this sequence? There are total. Okay. There are total n plus 1 states. Okay. So I can say this has n plus 1 states. So you tell me, can I guarantee that at least one state will repeat at least 2 times? Can I guarantee this? You tell me a simple point. You have a DFA with n states. In the DFA, you have n states and you have a string of length n. Now, if you run this DFA on this string, you will get a unique sequence of states. In this unique sequence, you will have n plus 1 states. Can I guarantee that in this sequence, at least one state will repeat at least 2 times? Okay, simple point. Yes or no? Because you only have n states. In your DFA, total n states you have. But how many you need? How many you need? You need n plus 1. You need n plus 1. So DFA has n states. You need n plus 1. So at least one state must repeat at least 2 times. Okay, so very simple. So I can say some state means at least one state repeats, or I can say occurs. Repeats, or I can say occurs. How many times? At least 2 times. At least 2 times. Okay, very simple. At least 2 times, some state will definitely occur at least 2 times. Okay, this is the point. Now you tell me one more thing. If I take the string length is, let's assume t. Let's assume string length is t, which is greater than n, which is greater than or equal to n. String length is t, which is greater than or equal to n. Now you run this DFA on this string W, then you will get a unique sequence. In this unique sequence, what will be the length? What will be the length of this unique sequence? That will be t plus 1. That will be t plus 1. So in this, that will be t plus 1. And t plus 1 is definitely greater than or equal to n plus 1. Yes or no? Correct. In this sequence, you have t plus 1 states, and we have already seen that. We have already taken that t plus 1 is greater than or equal to n plus 1. So your DFA has n states, but you need more than n states here. Yes or no? Basically, here you have more than n states. Basically, here you have more than n states. You have more than n states. Now you tell me, DFA has n states. You need more than n states. Then how can that happen? How will it happen? How can it happen? It will happen when you have at least one state repeats, at least one state, at least one state repeats, repeats at least 2 times. Correct? Is this point clear? So this is your simple observation. Please tell me, did you understand? So the point is quite simple, that you have a DFA, and this DFA has, let's assume you have a DFA M. You have a DFA M. Let's assume this DFA has n states. Now, if you take any string, okay, whatever string you take, for all W, whatever string you take, whose length is greater than or equal to n, okay, for all W whose length is greater than or equal to n, what will happen? What will happen for all such W? For every W whose length is greater than or equal to n, if you run this DFA, if you run this DFA on W, then what will happen? You will get a unique sequence. In that sequence, some state will repeat. Yes or no? You run this DFA, then definitely what will happen? Some state, at least one state repeats. Okay, I can say at least one state repeats. Is this point clear? At least one state will repeat. Let me know. Is this clear? So if you run this DFA M on W, then at least one state will repeat. Some state, some means at least one. Some means at least one. So at least one state will definitely repeat. Okay, so this is the point. I hope this point is clear. So this is your observation. You can easily notice D is a DFA. You have a DFA with n states. Okay, you have a string of length greater than or equal to n. This is your string. If you run this DFA on this string, then you will get a unique sequence of t plus 1 states. And in this sequence, what will happen? In this sequence, at least one state will repeat more than one time. Okay, yes or no? In this sequence, at least one state will repeat, will occur more than one time. Okay, means at least 2 times. So this is your observation. This is your final observation. Okay, you can here also you can check. Tell me your DFA has how many states? Tell me in the DFA how many states you have in the DFA? In this DFA, total you have 6 states. And what is the length of this string? What is the length of this string? What is the length of this string? That is 7. So can you guarantee, okay, without running, don't run the DFA on this string. Don't run. Okay, don't run this string. Don't run this DFA on this string. But can you guarantee at least one state will repeat? Tell me. Number of states is 6. The length of W is 7. Okay, so if you run this DFA M on this string, at least one state will repeat. Okay, tell me the sequence that you will get. How many states will be there in that sequence? In the sequence, how many states will be there? That will be 8. Okay, in the sequence, there will be total 8 states. So I can guarantee that at least one state will repeat. I can guarantee that. Okay, you can also notice here. Okay, at least one state is repeating. See, more than one state can also repeat. See, for example, Q2 is also repeating, Q1 is also repeating, Q3 is also repeating, but I care about at least one state. Agree or not? I only care about some state will repeat. You can notice some state is repeating. You can notice this Q1 is repeating. Okay, this Q1 is repeating. You can check. You can check this Q1, yellow color. This Q1 is repeating. Okay, so this is the simple point. Now, something very interesting is coming, and that will give you the feel of pumping lemma proof. Okay, that will give you the feel of pumping lemma proof. You tell me one thing. Okay, let's see. You tell me a simple point I want to ask. This length of the string is 7. Okay, now you tell me, and the number of states is 6. Can I guarantee that within the first 6 symbols, some state will repeat? See, this is your n. This is your n. Okay, can I guarantee the string length is 7? The string length is 7, but can I guarantee that within the first 6 symbols, some state will repeat? Means in this area, for these symbols, in this area, some state will repeat. Can I guarantee? See, okay, you also consider, basically, you also consider this also, means from here to here, from here to here. Okay, consider this. Are you getting my point? From from here to here, from here to here, can you guarantee that at least one state will repeat? Please tell me. Yes, definitely. Okay, yes, definitely. Here in this area also some state will definitely repeat. Okay, some state will definitely repeat. Okay, what is the reason? See, the reason is quite simple. Notice. If you have a DFA, let's assume the DFA has three states, or maybe you can take 4 states. Let's assume you have a DFA with the 4 states. This is your DFA. And let's assume you have a string. And this string has length, let's assume the string has length total 7. Okay, the string length is 7. Okay, now you know that this point is quite simple, that if you, this is your W, and if you run this DFA, if you run this DFA M on W, then in this sequence, this is the sequence that you will get. Okay, this is the sequence that you will get. This is the sequence. Okay, so you will get a sequence of states. Sequence of states. Sequence of states. So you will get this sequence of states. You will get a sequence of states. Now, see, in this sequence, what will be the length of this sequence? What will be the length? The length of this sequence will be 8. Now you tell me, this is quite simple. The length of the sequence means how many states are there in this sequence? In this sequence, we have total 8 states, but we only have 4 states. DFA has only 4 states. So at least one state will repeat. So I can say that in this sequence, at least one state will repeat. That is fine. At least one state repeats. At least one state repeats. This you already know. This is quite simple. But what I'm telling you that within the first 4 symbols, some state will repeat. But what I'm telling you, see something interesting. Within the first 4 symbols, this is your W. This W has total 7 symbols: A1, A2, A3, A4, A5, A6, A7. Okay, so this DFA has total 7, this string has total 7 symbols. This is your string W. Now, if you run this DFA, then you will get a sequence. You will get a sequence of states. When you run this DFA on this W, then you will get a sequence. Now you tell me what I am telling. I am telling that within the first 4 symbols, means from here to here, in this sequence, from here to here, in this sequence, some state will repeat. In this sequence means within the first 4 symbols, number of states is 4. Okay, number of states is 4. So within the first 4 symbols, some state repeats. Is this point clear? Some state repeats. What is the reason? Because if you take the first 4 symbols, okay, just to take the first 4 symbols, then tell me, for the first 4 symbols, what will be the length of the sequence? See, sequence is actually, this is your sequence. Your sequence is actually end here. Your sequence will actually end here. But you just tell me, you only tell me the length of sequence for the first 4 symbols. The length of the sequence, this is your sequence. See, this is the entire sequence. In this entire sequence, you tell me the length of the sequence for the first 4 symbols. That will be 5. Okay, that will be 5. So can I say in these 5 states, there are 5 states here. Can I say at least one state will repeat? Yes, because here you have 5 states. DFA has 4 states. So at least one state will repeat. Some state will repeat. Okay. Are you getting the feel of pumping lemma? In pumping lemma also, we are saying that within the first P symbols, okay, did you notice? In the pumping lemma statement, we were repeating within the first P symbols, Okay, so some connection we are making. Slowly, we are making some connection. So far, all the observations that you have taken, all these observations are very basic observations. You can also make, yes or no? There is nothing fancy. These observations that we are making, all these small observations that we are making, Tell me, are they fancy observations? Are they complicated observations? You can also make these observations by taking some examples. Okay, yes or no? So far, everything is clear. Let me know. Can I say so far everything is clear? So this is the point. Okay, so this is your final observation. As I told you, this is your final observation. So read this observation. Tell me, in this sequence, see, read this observation. You are running a DFA. DFA has n states, and the string has length greater than or equal to n. This string has length greater than or equal to n. If you run this DFA on this string, you will get a unique sequence. In this sequence, at least one state will repeat within the first n symbols. Tell me, did you understand? Within the first n symbols, some state will repeat. Means for the first n symbols, just look at the first n symbols. Only look at the first n symbols, some state will repeat. So this is the point. I hope this point is clear. So this, let me just make a diagram. So you have a DFA M, and in this DFA you have total n states, but your string length, what is that? That is t, which is greater than or equal to n. Okay, that is greater than or equal to n. Now, your string can be very long. I don't care. Your string can be very long. For example, your string has actually length t, a1, a2. You tell me one more thing. If string length is t, which is greater than or equal to n, then finally there will be at. Somewhere you will get an. Do you agree? Like this, if I do, somewhere you will get n. Like this, it will happen. Yes or no? Because t is greater than or equal to n. T is greater than or equal to n. So this is your string. Now, this is your string. Now you tell me, in this string, two things are happening. See, definitely you will get a sequence of states. You will get sequence of states. Now, this is the sequence of states you are getting. Okay, you are getting some sequence of states. So let me just write it in small. Okay, you are getting a sequence of states. So this white, or I can say from here to here, this is the sequence of states you are getting. This is the sequence of states. So you already know that what will be the length of this sequence? The length of this sequence will be t plus 1. And because this t plus 1 is greater than or equal to n plus 1, this t plus 1 is actually greater than n. Okay, this t plus 1, this is actually greater than n. Okay, so now you can easily notice some state repeats. Some state repeats. This is the one observation. The second observation is quite more interesting. What is that? The second observation says that you will get a sequence of states that is fine. Okay, you will get a sequence of states from here to here. You will get a sequence of states. But this second observation says that just consider the first n symbols. Only consider the first n symbols. Just consider these first n symbols. Is this clear? Just consider these first n symbols. That's it. Only consider these symbols. Now what will happen? Means in this area, just look at this area. In this area also some state will repeat. Okay, in this area, what are the length of this area, this restricted area? Means for the first n symbols, you will get n plus 1 length. Okay, n plus 1. So definitely DFA has n states, and in this area you have total n plus 1 states. So definitely some state repeats. So some state repeats for the first n symbols also. For the first n symbols also some state repeats. That's it. So using a diagram you can see. Using a diagram you can easily understand these observations. Okay, so very simple. Now let's move on. Okay, let's move on. Now we will see the pumping lemma proof, but before that I want to give you one analogy. Okay, because analogies are easy to understand, so that is the reason. So we will see the pumping lemma proof now. All the observations that we have made, these one by one I'm making observations. Yes or no? See, slowly I'm building to the pumping lemma proof. At the end we will see the pumping lemma proof, but before that one by one I'm making the observations. And let me tell you, I promise you, before I tell you the proof, you will understand the proof. Before telling the proof, you will automatically understand the proof. So one by one, all these small points that I'm telling you, did you understand one by one? We are building the house. We are building the house brick by brick. We are building the house brick by brick. So you tell me, are you understanding all these small points? Okay, let's see one analogy. This analogy, let's see. So you have a kid which is going to home from school. So let's assume there is a city. In this city, there is a kid. This is the school. This is the school. And here you have a kid A. Okay, let's call this kid, for example, maybe you can call this kid any name S. Okay, let's call this or P, whatever. Okay, so this is your kid. Now, this is the home. Home is the final state, right? Home is the final destination. Okay, from school, this kid is going to home. So this kid is going, but so there is this road. Let's call this road X. Now, at this point, there is friend's house. This is the friend's house. This P has a friend, and this is the friend's house. So this road, and let's call, okay, so let's call like this. And let's assume, so this entire thing, let's call it Y. Okay, means this is your road X, and this entire road, let's call it Y. And from here to here, this road, let's call it Z. Now, tell me one thing, what this child will do? This is a kid. This is a small kid. And what this kid will do? Will this kid go from school to home directly without going to friend's house? No, it will not happen. What this kid will do? This kid will do like this. First, it will take this road X, then it will take this road Y, and then it will take this road Z. Yes or no? This is what the kid will do. This is what the kid will do. So if the kid will do this, can I say it will reach the final destination? Tell me, will it reach the final destination? This home is the final destination. This home is your final state. This home is the final state. Okay, so if the kid will do this, then will it reach the home? Will it reach the final state? Yes, it will reach the final state. I can say, okay, I can say it will reach the final state. Now you tell me one thing. One day, what mother says, here mother is there. Okay, here you have the mother. Okay, one day what this mother says that come home directly. Okay, don't go there. Okay, so some kind of punishment. So come home directly. Now you tell me one thing. If this kid does not take this Y, can it go to final state? Means if this kid does not take this Y, just remove this Y. Okay, just remove this Y. So can it still go to final state? Yes, it can go to final state. Okay, very simple. Now you tell me one day what this kid is doing. Let's assume the summer vacation are going on. The summer vacation are going on. If this kid does like this, X, first you take X, then it takes Y. Okay, see, first you take X, then it takes Y, then it takes Y. Let's assume now he remembers that I forgot my bag. Okay, I forgot my tiffin at my friend's house. Now it again takes Y. It again takes Y. Then it takes Z. Can it go to final state? Still, can he go to final state? Yes, still he can go to final state. You tell me one thing. If you take this Y any number of times, if this kid repeats this Y any number of times, can still he go to final state? Means X, Y power N, Z. Can he still go to final state? This analogy, please understand this analogy and tell me, can this kid, can it go to final state? You can repeat this Y any number of times. Okay, so this analogy you understood? Did you understand this analogy? So from this analogy, you just have to remember that if you have this type of situation, okay, so consider this situation you consider. I'm just giving you a consider. If in your life, if you have this situation, let's assume this is Q0, this is your school. Let's assume this is in the analogy, this is the school. Okay, and you are taking this X, and here you are doing something, and this entire thing is called Y. And then you are taking Z. Okay, so let me use the different color. So you are doing something, that is Y. And then you are going to Z, and you are going to final state. And you are going to the final state. This is the final state. Okay, now just remember, whenever you have this type of situation in life, then you can simply observe that X, Y, Z will belong to final state. Okay, they will go to final state, yes or no? X, Y, Z will go to final state. If you repeat this Y 0 number of times, means X, Z, that will also go to final state. Okay, because what you can do, see, after taking X, once you come here, don't take Y, directly take Z. Okay, after taking X, after making X, if you come here, don't take Y, directly take Z, you can still go to final state. Okay, so this is what I'm saying. Next, if you repeat this Y 2 times, 3 times, okay, if you repeat this Y 2 times, then also you can go to final state. Similarly, 3 times, 4 times, 10 times, okay, any number of times, I can simply say any number of times you can still go to final states. Any number of times you can repeat this. You can repeat this Y any number of times. So just remember this diagram. This diagram, if we get this diagram in future, okay, today, if we get this type of diagram again, if this diagram I again get, then can you make these conclusions? Tell me, in future, today, if we get this diagram, if we get this diagram, then you can make these conclusions, right? Yes or no? Okay, so now let's make. So this analogy is over. This was just an analogy. This was not a concept. This was just analogy. Analogy is not a concept. So analogy is over. Now let's come back to concept. Now we are ready to understand the pumping lemma proof. The proof of pumping lemma, now we are ready to understand. So first you tell me what you need to prove. First, let's decide what we need to prove. This proof we will see, but actually what we need to prove. See, this is what we need to prove, right? We need to prove that if L is regular, then there is a magical number. Existence of magical number we have to prove, yes or no? Do you agree with me? What we have to prove? We have to prove the existence of magical number. Basically, what we need to prove for regular languages, existence of magical number. For regular language, existence of magical number we have to prove. Existence of magical number. Do you agree with me? Existence of magical number we have to prove. This is what we have to prove. Okay, so you already know the statement of pumping lemma. In the pumping lemma statement, what we have to prove? We have to prove that for any regular language, there exists a magical number n. There exists a magical number p. You can say there exists a magical number p, such that from that magical number this will happen, yes or no? For any regular language L, we have to prove that there exists a magical number. Existence of magical number we have to prove that there exists a magical number, such that what will happen? Such that for these strings which are in the language and have length greater than or equal to n, for these strings which belong to the language and whose length is greater than or equal to p, for these strings we have to prove that you can divide them into 3 parts. These strings can be broken into 3 pieces, x, y, z, okay, such that y is non-empty. Also, this xy, this part you can find within the first p symbols, and you can repeat this y any number of times. The result will also belong to L. So ultimately, this is what we need to prove. You already know this is what we need to prove. Now let's start. Okay, let's start. So take this example. Just take this example. Let's start and take this example. This is your DFA. This is the DFA. And this is your string. Now, tell me first of all, which strings we care about. Now onwards, which strings we care about. Now onwards, which strings I care about. Now onwards, first of all, we only care about regular language. We will only take regular languages. Now onwards, we will take regular languages. We will consider. What we will consider, tell me. Because we want to prove for regular languages. We will only consider. So tell me, from now onwards, what we will only consider? We will only consider regular languages, because we want to prove for regular languages. That's the simple point. We want to prove for regular languages. This is what we want to prove for regular languages. So we will only take regular languages. Second, which type of strings I will take? Which type of strings? We will only consider candidate strings. We will only consider candidate strings. Yes or no? We will only consider candidate strings, means those strings which belong to L and whose length is greater than or equal to P. But the point is, basically, I will only consider the strings which are in L. Yes or no? So this is the point. I will only consider strings which are in L and whose length is greater than or equal to P. This is what we will consider. Yes or no? Will I consider which strings, the strings which are not in L? Will I consider strings which are not in the language? Which are not in the language? I will not consider. I will only consider these strings. Okay. So very simple. These strings I will consider. Now let's start. First of all, you tell me, is this string belong to the language? This string, does it belong to the language? This string, will it belong to the language? Yes. You can notice this will belong to the language. Okay. This string will definitely belong to the language. Okay. So you tell me, number of states is how many? That is 6. What is the length of the string? That is 7. So can I say some state will repeat? Can you guarantee some state will repeat? Yes, some state will repeat because number of states 6, length of string 7. So the state sequence will have 8 states. Okay, you will get a sequence of states. In this sequence, you will have total 8 states. There will be total 8 states in this sequence. But DFA has 6 states. So at least one state will repeat. At least one state will repeat. You can check it out. Okay, at least one state will repeat. So tell me which state will repeat. This is your string. So 0, 0, 1, 1, 0, 1, 1, 1. This is your string. Okay, so tell me what sequence you will get. What will be the sequence that you are getting? You will start in state Q0. In this Q0, if you read 0, you will go to Q1. In this Q1, if you read 1, you will go to Q2. Then you will go to Q3. Then you will go to Q1. Then you will go to Q2. Then you will go to Q3. And from Q3, if you read 1, you will go to Q4. Okay. And this Q4 is the final state. Yes or no? This W is going to the final state. So far, everything is fine. I have taken this string. I have taken this string, and you can notice this string belongs to L. You can notice this string belongs to L because you are going to final state finally. Okay. Now something interesting. This state will repeat, right? See, this state is repeating. Notice this state is repeating. Agree? This state is repeating. Q1, Q1. This state is repeating. We already know some state will repeat. We already know. We already know some state repeats. This you already know some state repeats. Okay. Some state will repeat that you already know. And you can check this state is repeating. Okay. Now. When this state is repeating, for which part this is repeating? Between this repetition, Q1, Q1, between this repetition, this part, let's call it, this part, let's call it Y. Okay. Let's call it Y. And everything which is before Y, let's call it X. And everything which is after Y, let's call it Z. Okay. We are just calling it. So can I say W is actually equal to XYZ? So can I say W is actually equal to XYZ? Is this point clear? Did you understand? See, very simple point. This DFA is given to you and this string I have given to you. I am giving you this string. Now you run this DFA on this string. You will get a sequence of states. You will get this sequence of states. And you already know that some state will repeat. You already know. Okay, because in this sequence, there will be total 8 states, but DFA has 6 states. So at least one state will repeat. Some state will repeat that you already know. Okay, so you can see this Q1 is repeating. This Q1 is repeating. Now, before this Q1, this repetition, okay, between this repetition, between this repetition, you have some part of the string. This part of the string, let's call it Y. This part of the string, let's call it X, and this part of the string, let's call it Z. So I can say W is equal to what? W is equal to XYZ. Now, tell me. So can you notice what is happening? You will always start in the initial state. You are starting in the initial state. Then when you see 0, where are you going? Tell me. When you see 0, where are you going? You are going to Q1. In this Q1, you are seeing 1, 0, 1, 1, 0. Where are you going? Okay, in this Q0, you can read 0, you will go to Q1. In this Q1, after reading 110, where are you going? After reading 110, where are you going? After reading 110, you are going to Q1. And after that, if you read 111, where are you going? After that, if you read 111, where are you going? You are going to final state. You are going to final state. Okay, I can say you are going to final state. Do you remember I told you that if you see this type of diagram, you need to make some observations. You need to make some observations. You can easily notice this is what is happening. Your W is XYZ. Your W is XYZ. So 0, 110, then 111. Okay. This part we are calling it Y. This part we are calling it Z, and this part we are calling it X. So your W is basically XYZ. And what your DFA is doing? Your DFA is doing this. From the initial state, when you read this X, which is 0, when you read this X, you are basically going to state Q1. And in this state, when you read Y, in this state, when you read Y, you are going here. Okay, Y is 110. And from this state, when you read 111, you are going to final state. You are going to final state. This is what your string W is doing. Okay, your string W is doing this. Agree? Now tell me, if the string W is going to final state like this, first you take X, then you take Y, then you take Z. This is your string W. By doing this, are you going to final state? Means this string belongs to L. Yes or no? You are going to final state means this string belongs to L. You are going to final state means this string belongs to L. So tell me, can I say XZ will also belong to L? Can I say XZ will also take me final state? Tell me, can I say XZ will also take me to final state? XZ, don't take this Y. See, this just directly take 0, 1, 1. In this automata, just directly take 0, 1, 1, 1. Yes or no? So this 0, 1, 1, 1. See, from the initial state, 0, 1, 1, 1. This also belongs to the language. From the initial state, 0, 1, 1, 1. Yes or no? Agree or not? So can you notice that this is what I'm saying, that from this initial state, you can go to final state by doing this. First you take this X, then from this Q1, don't take Y, just directly take Z. Again, you are going to final state. If I take this Y again and again, will I still go to final state? Will I still go to final state? Will I still go to final state? Yes. Yes. If I take this Y 5 times, will I still go to final state? Will I still go to final state? Again, yes. So did you notice what this string is doing? This string is pumping, right? This belongs to L for all n greater than or equal to 0. You can repeat this Y any number of times. Your string will belong to the language. Is this point clear? So this string W, it is pumping, and this is a candidate string. Okay, this belongs to the language and this is pumping. Tell me this observation, did you understand? Please tell me, did you understand this? What is happening? Slowly, I am going towards the proof. But you understood this? Did you understand this? So quite simple, very easy. Okay, let's just take another example. Okay, consider this example. Now let me start. So far I am telling you that candidate string. So what are the two properties of candidate string? What are the two properties of candidate string W? What are those? One property, W should belong to the language, and another property is length of W should be greater than or equal to P. But what is P? But this is what we have to prove. We have to prove existence of P. We want to prove existence of P. This is what we want to prove. We want to prove existence of P. Yes or no? We want to prove this existence of this magical number. Okay. Now the important thing is coming. I am saying that number of states in DFA will definitely work as magical number. Okay. This is my claim. What is my claim? This is my claim. My claim, what is that? My claim is number of states in DFA will definitely work as magical number. This is my claim. Don't worry, I will prove my claim. But right now I am saying that number of states in DFA, number of states in DFA will work as pumping length, will work as P. This is my claim. Now we have to prove this claim. Okay. If I can prove this claim, then did I prove the existence of magical number? If I prove this claim, okay, number of states is equal to P. Number of states will work as P. If I prove this claim, then can I say that I have proven the existence of P? Yes, because for every regular language there will be DFA. Because what will happen? For every regular language, you can create a DFA. And in this DFA, the number of states will work as P. So for this regular language, you have a P. So for this regular language, there exists magical number P. There exists magical number P. Is this point clear? So all I need to do, what I need to do, I need to prove this, that number of states will work as P. This claim I have to prove. So now what we have to prove? Now we have to prove my claim. That's it. Okay, let's prove my claim now. Now we will prove my claim. So take this DFA. And what I'm saying, which P will work? Which P will work? Tell me. I'm saying P equal to 3 will work. Okay, let me prove it. Let me prove it that this will work. P equal to 3 will work. Let me prove it. Okay. So if I want to prove that P equal to 3 works, what that means? To show P equal to 3 works, what I need to do? I need to make sure that every candidate string pumps. If I want to show P equal to 3 works, then what I need to do? I need to show that every candidate string pumps. That every candidate string W, okay, every candidate string W pumps. This is what I need to prove, that every candidate string W pumps. And what that means? That means for every candidate string, what I have to show? I have to show that W can be written as XYZ. W can be written as XYZ, where Y must be non-empty. And I can repeat this Y any number of times. The result will belong to the language. And this XY must be within the first P symbols. These things I have to show. Okay. These things I have to show. Correct? Yes or no? Okay. Yes or no? Tell me. So let's see. P equal to 3. For this P equal to 3, now I will prove that every candidate string will pump. Every candidate string will pump. You tell me one thing. If P equal to 3, then which strings are candidate string? You just tell me which strings are candidate strings. Candidate strings. Strings which belong to L and whose length is greater than equal to 3. Give me such a string. These strings are the candidate string. These strings. Okay. Now you give me such a string. Give me one string. So take this candidate string, for example. Okay, take this candidate string 0, 1, 0, 1, 0. Take this candidate string. Let's start with this candidate string. Okay. I am saying P equal to 3. I am checking this P equal to 3. I am checking this P equal to 3. You take this string. You tell me one thing. What is the length of this string? Please tell me. What is the length of this string? The length of this string is 5. And what is the number of states in this DFA? That is 3. Now you tell me, can I guarantee some state will repeat? Can I guarantee some state will repeat? So I can say, when you run this M on W, then some state will repeat. Some state repeats. Some state repeats. Can I also say some state repeats for the first 3 symbols? For the first 3 symbols, can I also say that some state repeats for the first 3 symbols? Some state repeats for the first 3 symbols. for the first three symbols. For the first three symbols also some state repeats. I can also say this, some state repeats for the first three symbols. Okay, so let's check. So your initial state is A. When you read 0, you will go to B. When you read 1, you will go to B. When you read 0, you will go to C. When you read 1, you will go to C. When you read 0, you will go to A. And this is your final state. Yes or no? But you can notice for the first three symbols, some state has repeated. Which state has repeated? Some state has repeated. You can notice there is some repetition. Some state repeated. You can notice state B repeated. You can notice state B repeated. For the first three symbols, focus on the first three symbols. State B has repeated. Can you notice? So what happened? This is what happened. 0, 1, 0, 1, 0. Now, what happened? This was your initial state. You are going to B, then you are going to B, then you are going to C, C, A. Now, you can easily notice this state is repeating. This state is repeating. Between this state, what is the Y now? This state is repeating. Between this repetition, this we take as Y. Whatever is left of Y, that is X, and whatever is right of Y, that is Z. Correct? Yes or no? So this is the simple point, that your X is 0, your Y is 1, and your Z is 0, 1, 0. And can you notice from the initial state, this was your initial state. Your initial state was A. When you read 0, where are you going? When you read 0, where are you going? You are going to state B. Okay. So this, when you read this X, you are going to state B. In this state B, when you read Y, where are you going? You are going to B. Okay. And then tell me, if you read Z, where are you going? Then you are going to final state. Yes or no? Then you are going to final state, which is A. So this is the point. Now from this diagram, you can easily notice that this W, this is X, Y, Z. This belongs to the language. Okay. This means X, then Y, then Z. This belongs to the language. X, Y, then Z. Now you tell me, if I don't take this Y, then will it belong to the language? Will the resulting string belong to the language? Means you take this 0, then you directly take 0, 1, 0. Okay, don't take this Y. You take 0, 0, 1, 0. Check in this DFA. Check in this 0, 0, 1, 0. Will it be accepted? Check 0, 0, 1, 0. 0, 0, 1, 0. Is it accepted or not? Tell me. Is it accepted or not? You can check 0, 0, 1, 0. Yes, it is also accepted. So this is also accepted. Correct? So very simple. So this is what I'm saying, that you can notice if I don't take this Y, that is also accepted. This XZ is also accepted. If I take this Y multiple times, will it be accepted? Yes, it will be accepted. So can you notice X, Y power N, Z, that belongs to the language? So did I prove that this string is pumping? So we have proved that this string pumps. Yes or no? Agree? This string pumps. So what we have proved? We proved that this string pumps. We proved this W. Which W? 0, 1, 0, 1, 0. This string pumps. We proved that this string pumps. What that means? That means that for this W, what I can do? For this W, what I can do? I can break this W in three parts. Did you notice Y was non-empty? And also, did you notice that this XY, this repetition is happening within the first N symbols, within the first P symbols? Okay. And did you also notice that if you repeat this Y any number of times, the result belongs to the language? Okay. Yes or no? This is what we have done. I hope this point is clear. Now remember, whatever string you take, I am saying that whatever string you take, this will happen. For example, tell me which string should I take? I am saying that this P equal to 3 will work for this DFA. For this DFA, because number of states is 3, so P equal to 3 will work. So whatever string you take, that will pump. Whatever string you take, that will pump. So let me take this string, w equal to 0, 0, 0. Okay, you tell me one thing. Can you guarantee that some state will repeat? Forget about the DFA. Forget about the DFA. Number of states is 3. String has length 3. Can I guarantee some state will repeat? Forget about the DFA. Number of states is 3. String length is 3. Can you guarantee some state will repeat? Yes. Yes. And can you guarantee some state will repeat within the first 3 symbols? For the first 3 symbols, some state will repeat. Yes. Okay. So you can verify that. Now you can verify that. So you will start in the state A, then you will go to state B, then you will go to state C, then you will go to state A. Okay. This is what you are doing. And this is your final state. So what is happening? This string Y, sorry, this string W, what was happening? State A, then you go to state B, then you go to state C, then you go to state A. Now, this repetition is happening. You can check. You can check this repetition is happening. Between this repetition, what is Y now? Between this repetition, so your Y is this. So this is your Y. So your Y is 000. What is your X? X is empty string. What is your Z? Z is empty string. Okay, and did you notice that this W, what this W is doing? From the initial state, when you read empty string, where are you going? Because X is, when you read empty string, tell me, when you read empty string means when you read X, where are you going? When you read X, where are you going? When you read X, you are going to A. In this A, when you read Y, where are you going? In this A, when you read Y, you are going to state A. And in this state, if I read Z, then where are you going? You are going to final state. You are going to final state. Yes or no? The same diagram again you got. So this W, which is X, Y, Z, this belongs to the language. And can you notice, if I remove this Y, then can I go to the final state? Means if I don't take this Y, then XZ, will it belong to final state? Yes. You can check. Tell me, empty string is accepted or not? Yes, empty string is accepted. So you can verify. If I repeat this Y 2 times, that will also belong to L. Okay, this X, then you repeat this Y 2 times, then you go to final state. Is this point clear? So you can notice, first you take X, then you repeat this Y 2 times, then you take Z, then you will go to final state. So you can repeat this any number of times. So actually I can say X, Y power N, Z, that belongs to L. Okay, yes or no? N is greater than or equal to 0. So every string will pump. Do you agree? So this claim, did you understand this claim that number of states is 3? So P equal to 3 will definitely work. Please tell me, did you understand this? You can check this is working. Now let me give you the general solution. You understood the proof. The proof is over, but let me tell you the general template of the proof now. At this point of time, anyone has any doubt? Did you notice the pumping lemma statement that we have seen in previous classes? That statement we have almost proven. We have proven that statement. Anyone has any doubt right now? Everything that we have seen so far, anyone has any doubt right now? Tell me. Okay. If you have any doubt, just wait. Now let me tell you the entire proof. Now I am writing the entire proof. If they ask you in the interview, then you can say this proof. The proof. Tell me what we need to prove. We need to prove that regular languages satisfy pumping lemma. First, you tell me what we need to prove. Just tell me. The general proof I am giving you without examples. Without taking examples, the general proof I am giving you. What we need to prove? We need to prove that regular languages will satisfy pumping lemma. We need to prove that regular languages satisfy the pumping lemma condition. Satisfy pumping lemma conditions. Pumping lemma has some conditions, right? Okay, we need to prove that regular languages satisfy pumping lemma conditions. This is what we have to prove. Okay, that regular languages will satisfy pumping lemma conditions. So what I can do, instead of proving this, Can I directly prove that regular languages have a magical number? Can I directly prove? See, instead of proving this, regular languages satisfy pumping lemma. So to prove this, what I can do? To prove this, what I can do? Tell me. If I want to prove this, what I can do? I can prove that regular languages have some magical number. Have some magical number. Okay, yes or no? Have some magical number. And if I want to prove this, if I want to prove this, to prove this, what I can do? To prove this, I can prove that number of states will work as magical number. Yes or no? Did you notice? See, we want to prove regular languages satisfy pumping lemma conditions. To prove this, what I can do? I can prove that there is a magical number. There is a magical number. This is what I can prove. Okay. Now, if I want to prove that there is a magical number, if I want to prove that there is a magical number, then what I can do? Then I can simply prove that for regular language L, number of states in DFA will work as magical number. For regular language L, number of states in DFA, or I can say number of states in minimal DFA. Just take the minimal DFA directly. Okay, just take the minimal DFA directly. Is there a minimal DFA? Is it guaranteed that regular language will have minimal DFA? Is it guaranteed? Yes, it is guaranteed, right? So what we can prove? For regular language L, number of states in minimal DFA will definitely work as a pumping magical number. Will work as magical number. Will work as magical number P. Is this clear? Please tell me. Did you understand what I'm doing? This is your original problem. Your original problem is this. Prove that regular languages will satisfy all the pumping lemma conditions. Pumping lemma has some conditions. There are some conditions. This is what we have to prove. If you want to prove this, what I can do? To prove this, I can prove that regular languages have some magical number. Have some magical number. And to prove this, what I can do? To prove this, what I can do? I can prove that for any regular language L, the number of states in minimal DFA will work as a magical number. Now you tell me one thing, a simple question I'm asking. If I can prove that number of states in minimal DFA will work as P, then can I say I have proven the existence of magical number? If I can prove that for any regular language, number of states in minimal DFA is working as P, then did I prove the existence of magical number? Yes. Yes. Okay. So now let's prove. Okay. So what you do? You take any regular language. So let L be regular language. Let's L is a regular language. If it is a regular language, then there is a DFA. Then what will happen? Tell me. There exists a minimal DFA. If L is a regular language, then there is a minimal DFA. Tell me how many states will be there in the minimal DFA? Let's assume n states. Okay, so you can see there is a minimal DFA. There is a minimal DFA M. So L is a regular language. Then there exists a minimal DFA M. In this DFA M, in this minimal DFA M, let's assume the number of states. Number of states is n. Okay, let's assume number of states is n. Is this clear? Okay. Now I am saying that P equal to n will work. What I am saying? I am saying P equal to n will work. I am saying my claim that P equal to n will work. P equal to n works. Okay. Now let me prove my claim. The proof of my claim. So you tell me, in this language, I'm basically now I have to prove this P equal to n works. This is what we have to prove. Okay. Now let's see how to prove this. See, if you take any candidate string, because we only care about candidate strings. So take any candidate string, W. First of all, you tell me what are the properties of W? What are the properties of W? That W belongs to L. That W belongs to L and length of W is greater than or equal to P. These are the properties of W. Now I am saying that take any candidate string. Whatever candidate string W you will take. Then you tell me, if you take any candidate string, then what will happen? If you run this DFA, if you run this minimal DFA M on W, then tell me, can I say some state will repeat? Because remember, your minimal DFA has n states. Your minimal DFA has n states. And this length of W is actually greater than or equal to n. And I'm taking P equal to n. Okay. And I'm already taking P equal to n. So if I run this DFA on this string, this is your string. Your string is this. On this string. Okay. This is your string. Let's assume this string is like this. A1, A2, and so on, AN, and so on, AT. This is your string. Because the length of the string is, let's assume T. Let's assume the length of string is T, which is greater than or equal to n. Okay. The length of this string is T, which is greater than or equal to n. So this is your string. Now you tell me one thing. If you run this DFA M on this string, can I guarantee that some state will repeat? And one more thing. So you will start in the Q0. You will start in the Q0. Where you will go? You will go to Q final, right? Because this is a candidate string. Because this is a candidate string. This belongs to L. This string belongs to L. This string belongs to L. So you will go to final state, right? You will start in the initial state. In the initial state, you will start and you will go to final state. But between that, the length of the string, length of W is T, which is greater than or equal to n. Which is greater than or equal to n. So tell me, can I say that in this area, from here to here, can I guarantee some state will repeat? From here to here, for the first n symbols, tell me, for the first n symbols, can I say some state will repeat? Yes or no? I can say some state repeats. Some state repeats. This I'm telling you that some state repeats. This you already know. Okay, because in this area, how many states are there? In this area, how many states are there? In this area, for the first n symbols, how many states will be there? There will be n plus 1 states. But DFA has n states. DFA has n states. So definitely at least one state will repeat. Some state will repeat. Definitely some state will repeat. Some state will repeat. Okay. Now that's it. So you can notice in this W, this is your W. Your W is A1, then A2, and so on AN, and so on AT. This is your W. In this W, I am saying some state will repeat. At least one state will repeat. Let's assume that repetition is happening from let's assume the repetition is happening like this. See, some repetition will happen that you already know. Some repetition will happen that you already know. Okay, so let's assume that repetition is happening like this. Let's assume this is the repetition that is happening. Okay, this is the repetition happening because you already know some state will repeat. This you already know that some state will definitely repeat. Now let's assume that repetition is happening like this. Okay, that repetition is happening like this. Is this point clear? So tell me, which you will consider as Y? This is the repetition that is happening, Q. Then which state you will consider as Y? Which part you will consider as Y? See, this is what is happening. So tell me what you will consider as Y. Now you can consider between this repetition, this is what you can consider as Y, yes or no? I told you between this repetition, you consider this as Y. You consider this as Y. So what will be your X? What will be your X? This will be your X. So what will be your Z? What will be your Z? This will be your Z. Is this understood? So what is your X? See, X is A1, A2. And what is your Y? Your Y is A3 to AR. And what is your Z? Your Z is AR plus 1 to AT. Clear? Let me know. Is this clear? Some repetition will happen. You already know some repetition will happen. I am assuming that repetition is happening like this. Because anyway, some repetition will happen. Definitely some repetition will happen. And that repetition will happen within the first n symbols, right? Agree? Some repetition will definitely happen. And that repetition will happen within the first n symbols. Within the first n symbols, that repetition will happen. Within the first n symbols, that repetition will happen. So you can easily notice. So this is what you got. Now you tell me. That's it. Now you tell me. So this is what you got. You got that from the initial state. If I read X, where I am going? If I read X, where I am going? Tell me. If I read X from the initial state, if I read X, where I am going? Tell me. I am going to Q. I am going to Q. In this Q, if I read Y, in this state Q, if I read this Y, where I am going? I am again going to Q. In this state, if I read Y, then again I am going to Q. In this state Q, if I read Z, where I am going? I am going to final. I am going to final. Okay, yes or no? So I can say this W equal to X, Y, Z. This belongs to L. But can you notice? Quickly tell me, can you notice that I can repeat this Y 0 times? For example, if I directly take XZ, if I directly take XZ, will I go to final state? If I go like this, will I go to final state? Yes. And if I take this Y 2 times, then also I will go to final state. Yes or no? I can repeat this Y any number of times. I can repeat this Y any number of times. So I will definitely go to final state. So you can easily notice, your W. Okay, so you can easily notice Y, X, Y power N, that belongs to L for all N greater than or equal to 0. So basically what we did, we took a candidate string. Okay, what we did, tell me what we did. We did that we took candidate string, we took random candidate string, arbitrary. You can take any candidate string. Okay, we took random candidate string W. This is what we did. We took random candidate string W we took, and you already know the properties of W. This W has length greater than or equal to N. Okay, and this belongs to L. Okay, and I already said that P equal to N. I am checking P equal to N. So you can notice what we did. Now this W, we proved that this W can be broken like this. We proved that this W can be broken like this. We also proved that this XY part will be within the first N symbols. Yes or no? We already proved this repetition. This XY part will be within the first N symbols. And we have seen this Y is non-empty. This Y will definitely be non-empty. Why? Because if the state is repeating, then can it be non-empty? Can it be empty? If state is repeating, then this part we are calling it Y. This part we are calling it Y. And definitely this is non-empty. Yes or no? Agree? This Q is repeating. So in the string, this part we are calling it Y. So definitely Y will be non-empty. So you can notice Y is non-empty. And X, Y power N, Z, that belongs to L. Okay, that's it. So all these things, this is what we have proven. This is your proof of pumping lemma. And this is over. So tell me, did you understand? The proof was actually analytical. See, it is not a complicated proof. But please tell me, did you understand the proof of pumping lemma? Did you understand the proof of pumping lemma? And can you notice this is the proof? Okay, this is the proof. That's it. So we have proven the pumping lemma. I hope you understood. You can notice some state will repeat. You can notice some state will repeat for the candidate strings. For any candidate string. Here you can notice number of state is 6. The length of the string is 7. Some state will repeat. Now what you can do? You can consider this part as Y. You can consider this part, this 110, you can consider as Y. Now you can repeat it 0 times. If you repeat it 0 times, you will get this string. And if you repeat it multiple times, this Y, if you repeat multiple times, then that will also belong to the DFA. That will also belong to the language. So that's it. We have proven. This is your proof. Read this one time. Read this proof one time. Okay, let's read this proof one time. We have already proven, but read this proof one time. So let D be a DFA with n states. Now, if you take any string accepted by M, okay, if you take any string accepted by M, means W belongs to L, that has length at least n, means length of W is greater than or equal to n, then what will happen? Some state will be repeated. Then what will happen? Some state will be repeated. Yes or no? Correct? Okay. D is a DFA with n states. If you take any string which belongs to L and length is greater than or equal to n, then some state will be repeated. Now, you can easily notice number of states visited is equal to the length of string plus 1. Okay. Number of states visited, that is length of string plus 1. By pigeonhole principle, some state will repeat. Some state will repeat. Okay. Some state will repeat. Now you can notice the substring of W between these repeated states. Yes or no? See, what was Y? Do you remember what was Y? Some repetition will happen, but the substring which is between these revisited states can be removed, duplicated, tripled without changing the fact that D accept W. This is your proof. Please tell me, did you understand? The proof, did you understand? You have a DFA which has n states. If you take a string which belongs to L, whose length is greater than or equal to n, if you take this type of string, then what will happen? Then definitely some state will repeat. Okay, definitely some state will repeat. What will happen for this W? For this W, what will happen? Some state will repeat. A1, A2, and so on, AT. Somewhere some state will repeat. This repetition will happen. If this repetition happens, then this part you can take as Y. This part you can take as Y. This part you can take as X. And this part you can take as Z. Then what you can do? Then this Y you can repeat any number of times. This is your proof. You can read this. This is your proof. Please tell me, understood? Give me honest review. Did you understand? Honestly tell me, honestly. Did you understand the proof? Whatever we have seen in this class, every point, did you understand? Honesty is very important. Okay. Can you explain this proof to anyone? Can you explain this proof? Can you explain to anyone in the interview? When you go to some interview, IIT, ISC, MTech research interview, MS interview, or any job interview, PSU interview, if they ask you this proof, can you explain? Okay. So this was your proof. I hope you understood the proof. So what is happening? What is the proof? Let me just tell you. Okay. Verbally, I am telling you. Whatever regular language you have, there exists a minimal DFA. Agree? One by one, I am asking. Okay, just tell me agree or not. For any regular language L, there exists a minimal DFA. Now, in this minimal DFA, you have some number of states. That number of states will work as P. Okay, in this minimal DFA, you have number of states. That number of states will work as pumping length. That will work as magical number. Why? What is the reason? Let me tell you what is the reason. Let me tell you why. Because if you take any string whose length is greater than or equal to number of states, if you take any string, the number of states is n. Now, if you take any string whose length is greater than or equal to n, then what will happen? Some state will repeat. Agree? Some state will repeat. Within the first n symbols, some state will repeat. Your string can be very big. Your string can be very big, but within the first n symbols, some state will repeat. Now, when this state is repeating, this state Q is repeating, what you can do? You can take this, between this, state is repeating, between this you can take the substring you can take as Y. Whatever is left of Y, that you can take as X. Whatever is right of Y, that you can take as Z. Now, you can repeat this Y any number of times. You can repeat this Y any number of times. The resulting string will belong to language. Okay? Will belong to language. That's it. This is your proof. And tell me one more thing. If this state is repeating, this state Q that is repeating, is it guaranteed between this? Is it guaranteed you will have some non-empty portion? Means, is it guaranteed Y will be non-empty? Is it guaranteed y will be non-empty? Y will be non-empty. Why? Yes, because if state is repeating, state P, if state is repeating, then it means you have some non-empty portion between them. Okay, state P. If they are repeating, then you have some non-empty portion between them in the string. So y will be non-empty. Okay, so y will be non-empty. Y can be repeated any number of times, and this xy you will get within the first n symbols. Okay, this xy you will get within the first n symbols. So this is your proof. I hope you understood. If you understood, please comment on this video. Okay, because this is important for me. Your feedback is very important for me. If you understood, please comment on this video. I will put this video on GoClasses YouTube channel. Please comment on this video if you understood the proof. Okay. Now, let's move on. So we have already seen what is this pumping lemma. We have already seen the proof of pumping lemma. We have seen. Now, do you remember I told you that some questions you can solve only if you know the proof? Do you remember? There are some questions you can solve those questions only if you know the proof. So let me tell you the power of proof. The proof is also very powerful. Using proof, if you know the proof, if you understand the proof, then you can solve some questions. So let me tell you the power of proof. Okay, so let's see the power of proof. Let's see. Okay, so let's see the power of proof now. Tell me this question. What is the answer? What is the answer for this question? Read this question, tell me which statement is correct. Two statements are given to you. This question you read and tell me which statement is correct. Let me tell you, this is Cambridge University question. This is Cambridge University question. So tell me, is there any lagging? Today, is there any problem? Today, is there any lagging? Is there any voice breaking? Is there any issue today? Okay, very good. So tell me the answer for this question now. Remember this question, it is taken from Cambridge University. Okay, so tell me the answer. So the question, read this question. W is a string. M is n state DFA. What is M? M has n states. N states DFA. Okay, M is a DFA. M is a DFA that has n states. W is a string. W is a string. Suppose M accepts X. Okay, means this X belongs to LM. This X belongs to LM. You can notice M accepts X. So X belongs to LM. Length of X that is greater than or equal to N. That is greater than or equal to N. So tell me, is this X a candidate string? Is this X a candidate string? Yes, I told you, if you remember, I told you this N will work as P, right? Okay, this will definitely happen. Yes or no? This N will work as P. This N, number of states in DFA, that will work as P. So this X is a candidate string. So you can notice X belongs to L and length of X that is greater than or equal to P. So you can notice this X is a candidate string. X is a candidate string. So if X is a candidate string, then what we can do with X? Tell me. If X is a candidate string, then what we can do with X? We can divide this as XYZ, or I can say UVW, correct? We can divide this string X as three parts. Three parts we can create. UVW. Okay, now tell me, this V will be non-empty or not? This is your Y. So tell me, this V will be non-empty or not? Yes, V will be non-empty. And you tell me, U V power N W that belongs to that belongs to L. Yes or no? And also this UV, is this point clear so far? And this UV, this will be within the first P symbols. This will be within the first P symbols. We can do this, agree or not? Because X is a candidate string. So candidate string will pump. Because X is a candidate string. X is a candidate string, so it will definitely pump. It will definitely pump. So it will definitely broken into, can be broken. This candidate string can be broken into 3 pieces. Can be broken into 3 pieces. 3 pieces. What are those 3 pieces? U, V, W. The middle piece is your Y. So middle piece is non-empty. And you can repeat this middle piece any number of times. And this will be within the first P symbols. This will be within the first P symbols. So tell me, which statement is correct? P, Q. The only difference in this P, Q, what are the only difference? Tell me what is the only difference? What is the only difference? The only difference is here. The only difference is here. This is the only difference. Yes or no? If you notice, this is the only difference. There is only this difference you have. This difference, this is the only difference. This is the only difference. That's it. No other difference. No other difference. Okay. So the answer should be P, right? Let me tell you, the answer will also be Q. Okay. The answer will also be Q. If you know the proof, let me tell you, the answer will also be Q. Okay. Don't worry. I know. See, I already know you will give me answer equal to P. I already know. Okay. Don't worry. That is the reason I have taken this question. So if you did not give correct answer, don't worry about it. Let me tell you, the answer will also be Q. Why? What is the reason? Just remember the proof. You tell me. Okay, just remember the proof. You have a DFA. You have a DFA, some DFA D, minimal DFA, DFA, whatever. You can take any DFA D or DFA M. You have a DFA M. Now, you take any candidate string. So tell me, first of all, in this DFA, let's assume number of states is N. Will it work as P? In this DFA, you have number of states that will work as P. I told you that will work as P. Okay. So this number of states, this will definitely work as P. Now one more thing. If you take any such string, okay, for all such strings, what will happen? For all W which belong to L and whose length is greater than or equal to N. Okay. For all such W, what will happen? For all such W, such that, I can say, such that for all such W, what will happen? Some state will repeat, right? Yes or no? See, if your W has length T, let's assume A1, A2, and so on. Okay. And so on AT. So you tell me, do you remember? Tell me one interesting thing. I told you that within the first N symbols, some state will repeat. In our proof, what I told you? I told you within the first N symbols, some state will repeat. Here some state repeats. Here some state repeats. I told you this. I told you that some state will repeat within the first N symbols. So you tell me one thing. Just think about it. Within the first N symbols, if a state can repeat, within the first N symbols, then in the last N symbols, it will also repeat. Yes or no? Agree or not? In the last N symbols, tell me, is this point clear? What I'm saying? Let's assume these are the last N symbols. Let's assume these are the last N symbols. Let's take these last N symbols. Can you guarantee some state will repeat? Can you guarantee some state will repeat? Means from here to here. Can you guarantee some state will repeat? Ultimately, these are N symbols. So in this part, how many states will be there? Just tell me. In this part, how many states will be there? Again, N plus 1 states will be there. Because these are the last N symbols. So can I say some state will repeat here also? Can I say some state repeats here also in the last N symbols? Can I say? Is this clear? Can I say some state will repeat in the last N symbols? Focus on last N symbols. Focus on last n symbols. So can I say in the last n symbols also state will repeat? So notice. This is your string A1, A2, AI, and this is your AT. I told you that these are the last n symbols. Okay, these are the last n symbols. And some state will repeat here also. Okay, some state will repeat, right? Some state will repeat. For example, maybe this is AJ. Okay, maybe this is AJ, and I'm out of the vocabulary. Tell me some A, B, C, D, E, F, G, H, I, J, A, H. Okay, so let's take AH. Okay, now you tell me some state will repeat, right? Correct? Agree? Some state will repeat. So let's assume you know some state will repeat, that you already know. This you already know that some state will repeat. So let's assume that state is repeating from here to here. Let's assume that state is repeating from here to here. Because some state will repeat, that is a guarantee. This is guaranteed that you already know that some state will repeat in the last n symbols. Focus on the last n symbols, some state will repeat. So let's assume here the repetition is happening. Okay, now tell me which y I can take. Now tell me which y I will take. Focus on the last n symbols, some state is repeating. Now tell me which y I will take. Now which y I will take? I will take this y. Okay, between this repetition, this let me take as y. Whatever is on left of it, let me call that, whatever is on left of it, let me call that x. And whatever is on right of it, let me call it z. Okay, is this clear? And tell me one thing, which area will be less than equal to p? Can you notice that this yz will be within the last n symbols? Can you notice? Please tell me. Can you notice? This yz will be within the last n symbols. Agree? Yz will be within the last n symbols. Yes or no? Because only focus on last n symbols. We are only focusing on last n symbols. We are focusing on these last n symbols. So can you notice this yz will be within the last n symbols? Yes or no? Yz will be within the last n symbols, and y will be non-empty. Y cannot be empty because we are taking y equal to, between this repetition everything is y. Okay, between this repetition everything is y, so y is non-empty. Now can I repeat this y any number of times? See this diagram I am getting. Tell me. This w is your xyz, and this belongs to L. This belongs to L because this is a candidate string. So from the initial state, when you read x, where are you going? After reading x, where are you going? After reading x, this is your x. After reading x, where are you going? You are going to state q. In this x, after reading y, where are you going? After reading y, where are you going? In this x, in this q. In this q, after reading y, I am going to again q. I am again going to q. And in this q, if I read z, where I am going? I am going to final state. I am going to final state. Okay, so now you tell me, can I repeat this y any number of times? So I can repeat this y any number of times, and string will belong to L, and the resulting string will belong to L. Okay, so this is your proof. Did you notice what happened? That pumping lemma doesn't have one statement. Pumping lemma pumping lemma has many versions. Can you notice? Pumping lemma has many definitions. Did you notice? Pumping lemma has many definitions. This pumping lemma has many definitions, not one definition. Pumping lemma has definition 1. Definition 1 was the most popular. That is by default pumping lemma. Definition 1 is what we saw so far, what we studied most of the time. Pumping lemma definition 1, that is what we studied most of the time. Most of the time, the definition that we have seen, that is your pumping lemma definition 1. And this is by default definition. This is by default definition of pumping lemma. Are you getting my point? If they mention pumping lemma, then this definition you have to take. And we have seen another definition. Definition 2 also we have seen. Let me tell you the difference between these two definitions. This definition 2 we have seen just now. Actually, what happened? Some of you are not understanding, I know. So actually what happened, let me tell you. Let me tell you actually what happened. Okay. In our definition 1 of pumping lemma, what was happening? Tell me. In definition 1 of pumping lemma. In definition 1 of pumping lemma, what was happening? Tell me. In definition 1, okay, in definition 1 of pumping lemma, what was happening? In this, it was happening that pumping length P, in this it was happening that pumping length was P, then every candidate string, for every candidate string W, for every candidate string W, tell me what we were doing for the last three parts, part 1, part 2, part 3. So far, most of the time what we were doing, pumping length is P for every candidate string W, for every candidate string W. Okay, for every candidate string W means W belongs to L and length of W is greater than or equal to P. For every such string, what was happening? Tell me. This was happening that W can be broken into XYZ. W can be broken into XYZ. Yes or no? W can be broken into XYZ. Such that, what were the three conditions? The three conditions were Y is non-empty. Another condition was XY is within the first P symbols. XY that is within the first P symbols. And you can repeat this Y any number of times. The result will belong to L. You can repeat this Y any number of times. The result will belong to L. On your screen, what I have written, this is your by default definition of pumping lemma, right? Yes or no? This is what we have seen. This definition we have seen. We have taken many questions. We have taken many examples. We have become expert in this definition. Yes or no? You have become expert in this definition. You have become comfortable with this definition. But you can create many definitions from the proof. See, if you want to prove this definition, which symbols you were considering? Which n symbols you were considering? The first n symbols. Okay, when you, yes or no? So in the proof of pump, if you want to prove definition 1, if you want to prove definition 1, then what you can do? You can consider the first P symbols. Just consider the first P symbols. Yes or no? If you want to prove definition 1, consider first P symbols. Some repetition will happen. Yes or no? Consider first P symbols. Some state will repeat and you can prove. Agree? This is what we were doing. This is what we have done in the proof of pumping lemma. We were considering the first P symbols. In this first P symbols, some repetition was there. Some state was repeating. Some state repeated. And then we took XYZ. Then we take XYZ and like that. So this was your proof. Now, there is another definition of pumping lemma. What is that? In the another definition of pumping lemma means if I consider the last n symbols, then what will happen? If I consider the last n symbols, then what will happen? Tell me. Okay. In the proof of definition 2, what you can do? This is your pumping length was P. Okay. In the proof of definition 2, what you can do? So in this proof, what you can do? You can just take a candidate string and you can consider the last P symbols. Just consider the last P symbols. Again, some state will repeat. Correct? Just consider the last P symbols. Okay, consider last P symbols. Again, the state will repeat. If you consider the last P symbols, then also some state repeats. Then also some state will repeat. And if this state repeats, then you can create XYZ. Then you can create XYZ. This is your proof of definition 2. In the definition 2, you can break every candidate string, you can break as XYZ. And what are the properties? See, Y will be non-empty. This is the same. Also, you can repeat this Y any number of times. This is also same. What is the only difference in every definition? What is the only difference? What is the only difference in any definition? In any definition. That is, okay, this YZ, you can consider from the last n symbols. This YZ you can consider in the last p symbols. This is your definition too. Okay, this is the only difference. This is the only difference that you can if you consider the last n symbols, if you consider the last p symbols, then your YZ will be here. Within this area, you will have YZ. Okay, within this we have YZ. We have YZ. Okay, and in the definition 1, what was happening? In the definition 1, what was happening? Within the initial n symbols, within these n symbols, within here, we have XY. Okay, so this is the idea. Now tell me one thing. Definition 1 says, consider the first n symbols, their repetition will happen. Okay, definition 1. See, definition 1 says that consider the first n symbols, repetition will happen. Definition 2 says, consider the last n symbols, repetition will happen. Consider the last n symbols, repetition will happen. Now, what definition 3 will become? Now, can you make definition 3? Definition 1 is saying, consider first p symbols, repetition will happen. Consider first p symbols, repetition will happen. Repetition will happen. Definition 2 says, consider last p symbols. Consider last p symbols, repetition will happen. Consider last p symbols, repetition will happen. What definition 3 you can create? What definition 3 you can create? Take p symbols in the string anywhere. In the string, take p symbols consecutively. That's it. Take p symbols consecutively. That's it. Yes or no? In the definition 3, you can take any consecutive p symbols. Just take any consecutive p symbols. That's it. Any consecutive p symbols. Any consecutive p symbols you take. Can I say repetition will happen? Tell me. Can I say repetition will happen? See, your DFA has n states. Your DFA has n states, and I give you a string whose length is greater than n. If I give you a string whose length is greater than or equal to n, and you consider these n symbols, let's assume here you have some n symbols. Will some state repeat? Will some state repeat? Tell me. You consider n symbols anywhere. Will some state repeat from here to here? From here to here, will some state repeat? Yes, some state will repeat. Yes, some state again repeats. Some state will definitely repeat by pigeonhole principle. By pigeonhole principle, some state will repeat here also. Agree or not? So whatever n symbols you take, you just take by pigeonhole principle. By pigeonhole principle, DFA has n states. DFA has n states. If you take any consecutive n symbols, you take, some state will repeat by pigeonhole principle. Just apply the pigeonhole principle. Pigeonhole principle. Just apply the pigeonhole principle. Some state will repeat. So the third definition that you can create, take any consecutive p symbols. Take any consecutive p symbols. Here you can find y. Okay. Here you can find y. Whatever is left of it, let's call it x. Whatever is right of it, let's call it z. So what definition 3 you will get? If you do like this, now there is no restriction on where y will be. Yes or no? In the definition 3, no restriction on where y will be. No restriction on position of y. Yes or no? No restriction on position of y. On position of y. On positioning of y. Is this point clear? Please tell me. In this definition 3, there is no restriction on positioning of y. Y can be anywhere. So what definition 3 you will get? This is the definition 3 you will get. Tell me, what definition 3 you will get? This is the definition 3 you will get. See, कि pumping length is P. Pumping length is P. Okay. For any candidate string, what will happen? What will happen? For any candidate string, W, what will happen? Remember, W has length greater than or equal to P and W belongs to L. Okay. So for any candidate string, what will happen? This W you can break as XYZ. This W you can break as XYZ. Y definitely will be non-empty, right? Y definitely will be non-empty. And you can repeat this Y any number of times. That is also same. But now just remove that condition. Because now there is no restriction on positioning of Y. There is no restriction on positioning of Y. So that condition you can just remove. This is your definition number 3. Did you notice that another condition I removed? I removed that condition because that condition is putting restriction on where Y will be. Definition 1 says Y will be within the first P symbols. Definition 2 says Y will be within the last P symbols. And definition 3 says Y can be anywhere. Definition 3 says Y can be anywhere. So that second condition you can just remove. Don't put any restriction on positioning of Y. Don't put any restriction on location of Y. Y can be anywhere, but Y will be non-empty and you can repeat this Y any number of times. I promise you, these are the only definitions that are possible. Definition 1, definition 2, definition 3. So in the GATE exam, if they ask you some question on this, then only these 3 definitions will be there. You can notice this Peter Lynch question. This is Peter Lynch question number 14 in this Peter Lynch. Tell me, which definition is this? Prove the following version of pumping lemma. Prove the following version of pumping lemma. Which definition is this? This is your definition 2, yes or no? Can you notice this is your definition 2? This is your definition 2. Agree? Do you agree? Because this is saying if L is regular, then there is a magical number. There is a magical number such that whatever string you take in this language whose length is greater than M, what we can do? We can W can be written as XYZ, where this YZ is less than equal to M. Y is non-empty and you can repeat any number of times. This is your definition 2. Yes or no? This is a Peter Lynch question. So this question is there in the Cambridge University also. I told you this question was in the Cambridge University. So this question you can find in the Cambridge University. You can also find this question in your favorite, in your very easy book. This is the easy book of TOC. In this Peter Lynch also you can find this definition. The question is saying, prove this. How will you prove this? Tell me. How will you prove this definition 2? How will you prove this definition 2? Just consider the last n symbols in the candidate string. Yes or no? Just consider the last p symbols. Just consider the last p symbols. In these last p symbols, you can find Y. This will be Z and this will be X. So you can easily notice YZ is in the last p symbols. YZ, that will be in the last p symbols. Y is non-empty and you can repeat this Y any number of times. This is your proof. This is your proof. Did you see the power of proof? Please tell me. Please tell me. Sorry. Tell me. Did you see the power of proof? Some questions you can solve only if you know the proof, right? Some questions you can solve only if you know the proof. Now tell me one thing. This is Stanford University. This screenshot is from the Stanford University. Stanford. Tell me which definition is this? Read this and tell me which definition is this. This is the definition of pumping lemma. Which definition is this? Which definition of pumping lemma is this? This is the third definition of pumping lemma. This is the third definition of pumping lemma. In this definition, how will you prove this definition? How will you prove this definition 3? Tell me, if you want to prove this definition 3, then how will you do that? In this string, consider any p symbols. Consider any p symbols. Okay, just consider any p consecutive symbols. Consider any p consecutive symbols. Agree? Just consider any consecutive p symbols. So some repetition will happen, some state will repeat. The same idea. Some state will repeat. Then you can take y, This area you can call x, this area you can call z. So y will be non-empty, and you can repeat this y any number of times. You can repeat this y any number of times. This is your definition 3 of pumping lemma in your favorite Stanford University. Okay. In the Stanford University, they are calling it weak pumping lemma. See, okay. The Stanford University, they call this version, this definition 3, they are calling it weak pumping lemma. But don't worry. Don't worry about it. The point is, this is your definition 3. So pumping lemma has how many definitions? So pumping lemma has how many definitions? Tell me. So pumping lemma has 3 definitions, or I can say 3 versions. So pumping lemma has 3 versions: version 1, version 2, version 3. There are 3 versions of pumping lemma. This version 1, what is the by default version? In the exam, if they give you some question, and they give you this word pumping lemma, which definition you will use by default? Which definition? Yes, remember this version 1 is by default. Okay. So always remember, this is your by default version of pumping lemma. So in the GATE exam, if any question comes and they mention this word pumping lemma, they give you this word, this pumping lemma word is given, then which definition you will use? This first definition you will use. Okay, that is your by default definition. Okay, and these versions, I told you this version is given in which book? It is given in Cambridge University. This version I found in Cambridge plus Peter Lynch. In the Cambridge University plus Peter Lynch, this version is given. And this version is given in the Stanford. But tell me one thing. If you know the proof of version 1, if you understand the proof of first version, can you prove second version, third version? Please tell me. If you understand the proof, the first proof, the pumping lemma proof, if you understand, then very easily you can prove definition 2, definition 3. So this is your overall pumping lemma. We have finished the pumping lemma. Everything we have done. Some complicated questions also we have done. Let me tell you, these definition questions are extremely complicated, right? Just think about it. If these questions come in the GATE exam, okay, they give you MSQ. MSQ options are given. Then, for example, this question, notice this. For example, this question. Notice. If this type of question comes in the GATE exam, what majority of the students will do? They will say that this. But the answer is both this also, and you can make another version also. What another version you can make? You can make another version also. You can make version R also. Okay, you can make version R also. In that, you can just remove this. That's it. So this R is also correct. P is correct, Q is correct, R is also correct. Okay, clear? P, our definition 1. P is our definition 1, which is by default version of pumping lemma. By default version of pumping lemma. By default version of pumping lemma. This Q is definition 2. This Q is definition 2. And this R is your definition 3. That's it. So this type of question, if they ask you this type of question, then you can solve it. Okay. So at this point of time, I want to tell you, whatever question anyone can ask you from pumping lemma, in any interview, in the GATE exam, in TIFR exam, in any exam, whatever question anyone can ask you from the pumping lemma, from this concept, you can solve it. We have covered it. We have done the, I can say, complete analysis of pumping lemma we have done. Okay. There is a dialogue, dhaga khol dena. Okay. So just like every other topic, in every subject we do this. Okay. So the same thing we have done in the pumping lemma also. Please tell me your feedback of pumping lemma. I request you to comment your feedback of pumping lemma under this video. This is our final part. Okay. I can say this is your part 4. Pumping lemma is over. We have done the pumping lemma. If you want, I can take some practice questions. Okay. We can take some practice questions if you want. One session, we can take only 4 questions. Okay. Only 4 questions. Back to back, we can solve a lot of questions we can solve. Okay. We can do that in the next 2-3 days. So I request you all to please comment your feedback of pumping lemma. Please comment. Okay. Will you do that? Will you do that? So this video, this part 4, I will put on the GoClasses YouTube channel. Please put your feedback of pumping lemma. Okay. Whatever you understood, how much you understood. So give me your detailed feedback of pumping lemma. And one more session. Now, 2 things I'm thinking what we can do. I can give you a weekly quiz for pumping lemma. In that weekly quiz, there will be 15 questions. Those 15 questions will cover every variety of question. Okay. Basically, every type of question that can be created, I will put in that weekly quiz. Okay. So that weekly quiz you can try. Okay. Is that clear? So, and one session I can take for practice. So 2 things are remaining. One thing is weekly quiz and one session is practice session of pumping lemma. So 2 things are remaining. So I will let you know. Okay. The practice session we will have in the next 2-3 days. We can have a practice session or we can have it tomorrow if you want. Okay. So let me know when you want this practice session to happen. I will take a lot of questions, different variety of different type of questions I will take and I will solve those questions. So this practice session, when should we have it? So let's have this practice session in the, I can say, maybe we can keep maybe day after tomorrow. Okay. Day after tomorrow, we can keep it. Okay, everyone. So let me just write it here. What things are remaining? We have to do. This is what we have to do. There will be one weekly quiz. This weekly quiz only on pumping lemma. There will be 15 questions on pumping lemma. Okay. And one session we will have a practice session. One practice session we will have. Okay. So this is what we will have. Okay. So we can do it. Both these things, these 2 things we can do on Sunday. Okay. We can have this practice session on Sunday. This practice session we can have on Sunday. Okay. Okay. Thank you, everyone. So please comment your feedback of pumping lemma. Okay. So thank you.